Welcome to Sleepy Astronomy, where space gets quiet and big questions come gently to life. Tonight we're shrinking down, not to the size of planets or stars, but to something much smaller. We're diving into the tiny building blocks that make up everything you've ever seen and everything you've ever been. Before we begin, let us know where you're watching from and what time it is for you right now. Comment below and settle in for a relaxing journey. Everything around you, the air, your pillow, even your heartbeat, is made of atoms. These tiny particles are older than the Earth itself. But where did they come from? And how do they work so perfectly, with electrons dancing endlessly around a centre that never pulls them in? Could the universe itself be acting like one giant atom? In this video we'll explore how these mysterious particles were born from nothing, how they shape the stars, and how they hold the entire universe together. Quantum fluctuations are the result of one of the most basic rules in physics, Heisenberg's uncertainty principle. This rule says that at the smallest levels of reality, it is impossible to know both the energy and time of a particle with complete accuracy. Because of this, tiny particles and energy waves keep appearing and disappearing in a restless dance of creation and destruction. Even in a perfect vacuum, where no matter exists, these changes still happen. Virtual particles, tiny, short-lived bits of energy, pop in and out of existence for tiny moments before disappearing again. These changes are not just ideas in theory. Scientists have seen their effects in experiments. They are the reason why atoms do not fall apart and why some particles act in ways that can't be explained using old-fashioned physics. Before the Big Bang, these quantum changes were everywhere. But at some point, something amazing happened. An event so strong that it turned these tiny ripples into the first steps of our universe. Scientists believe that a fast spread called cosmic inflation played an important part. During inflation, the universe grew at an unbelievably fast speed, stretching quantum changes across huge distances. These tiny changes, once stuck at very small sizes, were now enlarged, making differences in the fabric of space itself. As the universe cooled down, these energy changes became the plan for everything that would come later. The slightly thicker parts of space pulled in more energy, forming the first building blocks of a matter. In this way, quantum changes, once small flickers of doubt, became the base for galaxies, stars, and planets. Within the first millionths of a second of the universe's life, the high energy began turning into the most basic building blocks of matter. These included quarks, the tiny particles that would later join to form protons and neutrons; leptons, which include electrons, the particles that move around atomic centers; gluons, which acted as the glue that held quarks together. At this time, the universe was still a hot, thick mix, with particles crashing into each other at amazing speeds. But as it cooled down more, something wonderful happened. Quarks joined to form protons and neutrons, the key parts of atomic centers. About 380,000 years after the Big Bang, the universe had cooled enough for protons and neutrons to capture electrons, making the first steady atoms. This process is called recombination. The most common element to form was hydrogen, then helium, and a small amount of lithium. At this moment, the universe changed from a wild, energetic soup into something more organized. For the first time, light could move freely through space, leading to the release of what scientists call the cosmic microwave background radiation, a weak glow of energy that still exists today, showing us a picture of the early universe. While the making of atoms was an important step, the universe was still far from what we see now. These early atoms were spread out in space, floating in huge clouds of gas. Over millions of years, gravity began to pull these atoms together, forming big clumps. In some places, gravity was so strong that it squeezed atoms closer and closer, heating them up and starting nuclear fusion. This was the birth of the first stars. Inside these early stars, nuclear reactions joined hydrogen and helium atoms into heavier elements like carbon, oxygen, and iron, the very things that make up planets and even life. When these stars reached the end of their lives, they exploded as supernovae, spreading these elements into space. Over billions of years, this space dust came together into new stars, planets, and in the end, the Earth itself. It is amazing to think that everything around us, from the air we breathe to the stars in the sky, can be traced back to tiny quantum changes in the universe's first moments. These changes, once random and hard to predict, became the base for galaxies, planets, and life itself. Without them, the universe might have stayed a smooth, empty stretch of energy, never making the complex things we see today. It was the small bumps made by quantum changes that let matter stick together, leading to everything we know and feel. The story of the universe is a story of change, of energy turning into matter, of simple atoms forming complex things, and of the tiniest changes shaping the largest parts of the cosmos. Quantum changes, once thought to be random noise, played a key role in this amazing process. Even today, quantum physics keeps challenging how we understand reality. It tells us that at the deepest level everything is unsure, yet this very uncertainty led to the making of something as huge and wonderful as the universe. Imagine a world where things can suddenly pop in and out of being, where something can be in two places at the same time, and where things act in ways that go completely against common sense. This is not science fiction. This is the strange and amazing world of quantum physics, a part of science that explains how the tiniest parts of our universe act. Unlike the world we see every day, where things follow clear paths and rules, the quantum world is full of surprises, mystery, and often acts in very odd ways. In this tiny world, particles, the small parts that make up atoms, do not always act like solid things. Instead, they act like waves of energy, always changing, showing up, disappearing, and even being in more than one place at once. How is this possible? How can something vanish and come back? To really understand this, we need to take a journey into the quantum world and learn about some of its most mind-blowing secrets. To understand quantum physics, we first need to look at the size we're talking about. Atoms, the tiny parts that make up everything, are already extremely small, so small that millions of them could fit on the tip of a pin. But atoms themselves are made up of even smaller parts, electrons, protons, and neutrons. And if we go even deeper, we find even smaller pieces like quarks and photons, which act in ways that go against normal thinking. In the world of quantum physics, these tiny parts do not act like little balls or pieces of dust. Instead, they act more like waves of energy that can move in strange and unpredictable ways. This idea is called wave-particle duality, meaning that these parts can sometimes act like solid things, and other times like waves of pure energy. One of the oddest things in quantum physics is how particles can seem to appear and disappear at random. This happens because of something called quantum changes. Even in the emptiest space, where we would expect total nothing, tiny particles are always popping in and out of being. These are called virtual particles, and they exist for only a very short moment before disappearing again. This may sound impossible, but tests have shown that these little bursts of energy happen all the time. How does this happen? According to quantum physics, empty space is not really empty. It is filled with quantum fields, invisible energy fields that fill the whole universe. These fields are always moving, and sometimes, just for a moment, they create tiny particles out of nowhere. These particles flash into being and then vanish before we can fully see them. This strange effect has real results. Experts believe that quantum changes helped shape the early universe. In fact, without these particles showing up and disappearing, the universe as we know it might not exist. To see just how strange quantum physics can be, let's look at a famous thought test by scientist Erwin Schrödinger. He imagined a story with a cat inside a closed box, along with a device that lets out poison based on how a tiny quantum particle acts. According to quantum physics, before we open the box to check, the cat is not just alive or just dead, it is in both states at the same time. This is because the small particle that controls the poison follows quantum rules, which means it can be in two states at once until someone looks at it. This strange idea, known as superposition, says that things in the quantum world are in more than one state until they are looked at or measured. While Schrödinger's cat is just a made-up story, the idea behind it has been tested in real studies with tiny particles. Scientists have seen electrons and photons acting in more than one way at once, only picking one clear state when someone measures them. Another odd and amazing part of the quantum world is quantum tunneling. In the everyday world, if you throw a ball at a wall, it will hit the wall and stop. But in the quantum world, a particle might pass through the wall like a ghost. This happens because, in quantum physics, Particles are not just tiny dots, they also act like waves. These waves can stretch beyond walls, meaning there is a small chance that the particle can tunnel through and show up on the other side. Quantum tunneling is not just an idea, it is real and used in tech. Today's electronics, like the small parts inside your computer and phone, use quantum tunneling to work. Without it, much of today's tech would not exist. One of the most important and puzzling ideas in quantum physics is Heisenberg's uncertainty rule. This rule says there is a natural limit to how well we can measure some things about a particle. For example, if we try to find the exact spot of an electron, we lose details about how fast it is moving. If we measure its speed, we lose details about its spot. This confusion is not because of bad tools, it is part of how reality works. This means that, in the quantum world, the universe is not solid and sure like what we see around us. Instead, it is a shifting, uncertain place where things happen as chances instead of clear events. One of the weirdest and most amazing parts of quantum physics is quantum entanglement. This happens when two particles become strangely connected, so that no matter how far they are from each other, a change to one instantly changes the other. If one particle is found spinning in one way, the other, no matter if it is across the universe, will instantly spin the other way. This happens faster than the speed of light, breaking what we thought were the limits of science. Albert Einstein famously called this spooky action at a distance. Even though it sounds impossible, entanglement has been proven many times. Scientists are even looking at how to use it for super safe ways to talk, and even future quantum computers. While quantum physics may sound strange and confusing, it is already shaping what's to come. Experts are working on quantum computers, which use quantum particles to handle information in ways that normal computers cannot. These computers could change everything from healthcare to smart machines. Quantum physics is also being looked at for new ways to make energy, super safe coding, and even the dream of teleportation. While moving people like in movies is still just a dream, scientists have already moved tiny particles using quantum entanglement. To understand quantum changes, let's begin with a simple idea. Empty space is not really empty. Even in a place with no air, light, or particles, something is still happening. Quantum physics, the part of science that studies the smallest parts of everything, tells us that space is filled with an invisible energy field called the quantum field. This field is never still. It always moves and shifts because of how random quantum physics can be. A quantum change is a tiny, short-lived shift in energy that happens in this field. Think of a calm pond. If you toss a stone in, ripples spread out. These ripples are like the small changes, just like quantum changes are small shifts in the energy field of space. The difference is that in quantum science, these shifts happen all by themselves. They just pop in and out on their own. At first, the idea that something can come from nothing might seem crazy. In our daily lives, things don't just appear out of nowhere. But in the quantum world, the rules are very different from what we see each day. The key to understanding this is a basic rule of quantum physics called the Heisenberg uncertainty rule. This rule says that some parts of a particle, like energy and time, cannot both be known exactly at the same time. Because of this rule, for tiny short moments, energy can exist where there was none before. These small energy blips sometimes turn into pairs of particles, one normal and one antiparticle, that last for just a tiny bit of time before disappearing again. These virtual particles are always appearing and disappearing, which means that at the smallest level, space is never really empty. Even in a vacuum, these particles flicker in and out of being, making nothing much more complex than we used to think. Quantum changes are not just strange ideas, they help shape the universe as we see it today. Here are some ways these tiny energy bursts have had a huge effect. One exciting idea in space science is that the whole universe may have started from a quantum change. Scientists think that before the Big Bang, the universe was in a very unstable quantum state. A tiny shift in that state may have caused the huge burst of energy that made the universe. This idea says that the universe didn't need something before it to begin. It could have simply come from the quantum vacuum because of the basic rules of science. If this is true, then everything we see, from stars to people, may have started as one tiny fast energy spark. Quantum changes also helped shape the layout of the universe. In the first moments after the Big Bang, small energy changes in the quantum field caused little differences in how thick or heavy some areas were. Over time, these little differences grew into big things like galaxies, stars, and planets. Without these quantum changes, the universe might have stayed smooth and plain, never growing the rich mix of things we see now. In a way, the whole cosmic web, the huge stretch of galaxies across billions of light years, owes its existence to the wild nature of quantum science. Black holes are some of the strangest things in space, but even they are affected by quantum changes. Stephen Hawking, one of the greatest scientists ever, said that black holes slowly lose energy and shrink over time because of something called Hawking radiation. According to this idea, pairs of virtual particles made by quantum changes can sometimes be pulled apart at the edge of a black hole. One particle falls in, while the other escapes, causing the black hole to lose a small bit of weight. Over huge amounts of time, this slow loss might even make the black hole disappear. You might ask, do quantum changes affect our daily lives? While they mostly work at a level too tiny for us to see, they do play a part in real things. One example is how atoms stay stable. Quantum changes affect how tiny parts of atoms act, which affects how atoms stick together. Without these changes, the basic forces of nature might work differently, and matter as we know it might not be able to exist. Another cool example is quantum computers. These new machines use quantum changes to work with information in ways that normal computers cannot. By using the odd parts of quantum physics, experts are building computers that could one day change fields like data safety, smart tech, and science. If tiny quantum changes can make particles, could a bigger change make something as huge as a whole new universe? Some scientists think yes. There is a theory called eternal inflation, which says that our universe is just one of many made by quantum changes in a never-ending growing space. In this view, new universes might be forming all the time, each with its own rules. The idea that tiny energy flashes can make matter from nothing is one of the most exciting ideas in today's science. Quantum changes challenge what we think is real, showing us that the universe is far weirder and more amazing than we ever dreamed. These tiny, fast energy flashes help shape everything, from the smallest parts to the biggest galaxies. They may have even helped create the universe itself. While we still have a lot to learn about quantum science, one thing is sure. The idea that something can come from nothing is not just a dream. It's a real part of how our universe works. Atoms, the tiny parts of everything we see around us, exist because of an amazing and delicate process that happened in the early universe. But to understand how atoms came to be, we must first explore an important thing: changes. These tiny random energy shifts played a huge part in shaping the universe and making atoms possible. At the start, the universe was like a boiling pot of energy, where particles kept bumping into each other and changing form. But this energy wasn't spread out evenly. Some spots had a little more energy, while others had a little less. These small differences, or changes, might seem tiny, but they were key to how the universe would grow. Think of these changes as small ripples in the fabric of space, caused by natural shifts in energy. These ripples happened because of a basic rule in science called quantum physics, which says that energy and matter are never perfectly the same at the smallest level. Even in what seems like empty space, little changes are always happening. In the super hot and dense early universe, these ripples were stretched and made bigger as space grew. Some spots got a bit thicker, meaning they had more matter and energy. Over time, these small differences became the starting points for everything, showing where stars, galaxies, and even atoms would appear. As the universe kept growing and cooling, something amazing happened. Energy started turning into matter. This happened because of the famous rule E equals mc squared, made by Albert Einstein, which says that energy can become mass. But this didn't happen smoothly or all at once. It depended a lot on the earlier changes. In spots where there was a little more energy, more particles could form. These thicker areas became the first places where tiny parts like quarks and gluons joined to make the parts of atoms. In the first millionths of a second, quarks joined to form protons and neutrons, the heart parts of atomic centers. But the process didn't end there. For atoms to form, protons and neutrons needed to grab electrons to become full atoms. But in the hot early universe, free electrons were moving too fast to join with atomic centers. The whole universe was like a thick soup of charged particles, where light couldn't travel freely because it kept hitting free electrons. After hundreds of thousands of years of cooling, the universe finally got cool enough for electrons to slow down and join atomic centers. This time is called recombination, and it marked the true birth of the first atoms. With electrons now stuck to centers, the universe became clear for light to travel. This light, known today as the cosmic microwave background, is still around and gives us a picture of the early universe. The first atoms were the simplest ones, hydrogen and helium. These made up 99% of the universe's atoms. Over time, gravity pulled these atoms into big clouds of gas, which later became the first stars and galaxies. If the early universe had been perfectly smooth, with no changes, matter would have stayed spread out. There would have been no thick spots where gravity could start pulling atoms together, and without that, no stars, planets, or galaxies would have formed. These tiny changes were like seeds, giving gravity something to work on. In places with a little more matter, gravity pulled in even more. This snowball effect made stars, which then made heavier elements like carbon, oxygen, and iron, the things we need for life. The Big Bang is one of the most important ideas in science, explaining how the universe began. Imagine everything in the universe, every star, planet, and galaxy, being packed into one tiny, incredibly hot and thick point. Around 13.8 billion years ago, this point suddenly blew up, sending everything outward in all directions. This event is known as the Big Bang, and it marks the start of time itself. In the moments after the Big Bang, the universe was extremely hot. It was like a huge, glowing ball of energy in tiny pieces. In fact, it was so hot that atoms couldn't even form yet. Instead, the universe was full of a soup of smaller particles, like protons, neutrons, and electrons, all rushing around at very high speeds. Over time, as the universe grew and cooled down, these particles began to slow and come together, forming the first simple atoms like hydrogen and helium. As the universe kept growing, gravity began pulling these atoms together, creating the first stars. These stars were huge, shining bright and hot, and they formed groups that later became galaxies. Galaxies are giant groups of stars, gas, dust, and other space stuff, and they spread out across the universe like islands in a big ocean of space. The result of the Big Bang is still happening today. The universe is still growing, which means galaxies are slowly moving farther away from each other. This was discovered by space scientists in the 1920s, and it's one of the most surprising things about the Big Bang. It's like every galaxy is moving away from us, like a balloon getting bigger. This idea has made scientists wonder about what might happen to the universe in the future. Will it keep growing forever, or will it one day slow down and fall back in on itself? Nobody knows for sure, but it's one of the biggest puzzles in today's science. The result of the Big Bang didn't just shape the universe's size and shape, but it also helped create the things we see around us. Stars and galaxies later gave rise to planets, including Earth. The elements that formed in stars became the basic parts of life, allowing life to start on planets like ours. In a way, the Big Bang not only made the universe, but it also gave us everything that lets us exist. By studying the Big Bang, scientists have learned a lot about how the universe started and how it keeps changing. The proof is all around us, from the faint glow of leftover light from the Big Bang, called the cosmic microwave background, to how galaxies move away from each other. These hints help us piece together the story of how the universe was born, how it grew, and how it's still changing over time. Where the universe came from has been something people have wondered about for hundreds of years, but science has found an amazing idea that helps explain how everything we know began. This idea is called the Big Bang Theory, and it gives us a mind-blowing look into how the universe started. Let's explain it in simpler words and talk more about how the universe started from a tiny, very hot and thick point. Imagine everything in the universe, every galaxy, star, planet, and even the empty space between them, was once squeezed into a single, incredibly small point. This point was so small that it's hard to even picture it. It's tough to understand how something as huge as the whole universe could fit into something so tiny. But that's where the story begins. Before the universe began, there was no space like we know it. Time didn't exist either. In other words, there was no before the Big Bang, because time started with the Big Bang. Everything, space, time, and matter, was packed into that tiny point. It was so hot and thick that it was like the whole universe was squeezed into a space too small to imagine. Around 13.8 billion years ago, this tiny thick point began to grow very fast. The name Big Bang means this huge event, the stretching out from a very hot, small and thick state to the universe we see today. It wasn't an explosion like a bomb. Instead, it was more like space itself started to stretch, carrying everything with it. This stretching happened extremely fast, even faster than the speed of light. Scientists call it inflation. In the first moments after the Big Bang, the universe was extremely hot, hotter than anything we can experience today. Imagine heat so high that even atoms couldn't form. The universe was filled with a glowing soup of tiny particles. These particles were too full of energy to stick together, but as the universe cooled down, they started to join, forming the simplest elements like hydrogen and helium. As the universe kept growing, it also kept cooling. In the first few minutes, it got cool enough for atomic centers to form. These centers, mainly hydrogen and helium, came together to build the first parts of stars and galaxies. For the first few 100,000 years, the universe was a foggy, glowing mix of hot particles and light couldn't move freely. This time is called the era of recombination. But as the universe kept growing and cooling, it finally became clear enough for light to travel. This moment gave us the cosmic microwave background, which we can still see today using special tools. This light is like a picture of the universe when it was only about 380,000 years old, showing us what it looked like in its early days. After the universe cooled enough to let light travel, the next big thing was the forming of galaxies and stars. As the tiny bits and gas were pulled together by gravity, they turned into big clouds of gas. These gas clouds then shrank inward and formed stars. These stars became the center of galaxies, and these galaxies joined together to create even larger groups in space. In the early galaxies, stars were often much bigger and hotter than today's stars. These stars didn't live long and exploded in huge events called supernovae. When these stars blew up, they spread heavy elements like carbon, oxygen, and iron throughout the universe. These elements became the basic parts of new stars, planets, and even life. Even now, the universe is still getting bigger. This was one of the most surprising things scientists found. Galaxies are moving away from each other, and the farther a galaxy is, the faster it's moving away. This shows that the universe is still stretching, just like it was in the beginning. This stretching doesn't mean that galaxies are flying apart through space. Instead, space itself is growing, and everything in it is getting farther apart. A good example is a balloon. Think of the universe as the skin of a balloon, and the galaxies as tiny dots on it. As the balloon gets bigger, the dots move apart. In the same way, as the universe grows, galaxies move farther from each other. While we've learned a lot about the universe, there's still much we don't understand. Two strange forces, dark matter and dark energy, are very important in the universe's growth. These forces make up a big part of the universe's stuff and energy, but they don't interact with light, so we can't see them. We can only notice what they do to galaxies and other space objects. Dark matter is thought to be the reason galaxies spin the way they do. Without dark matter, galaxies would fall apart because they don't have enough visible stuff to keep them together. Dark energy, on the other hand, seems to be making the universe's growth speed up. Scientists aren't totally sure what these things are, but they are very important in how the universe works. The universe has billions of galaxies, each with billions or even trillions of stars. Our own galaxy, the Milky Way, is just one of them. Over billions of years, galaxies have crashed into each other and joined together, making the huge, varied space we see now. This never-ending cycle of making, growing, and breaking down is what shapes the universe and gives us the amazing mix of stars, planets, and other things we see. One of the most mind-blowing things about the universe is how huge it is. Even though the universe is growing, the spaces between things like galaxies are so huge that we can barely understand them. The Milky Way is over 100,000 light-years wide, and light travels at about 186,000 miles per second. Yet even at that speed, it would take more than 100,000 years for light to cross our galaxy. As the universe keeps growing, scientists also wonder how it will end. Some ideas say it might keep growing forever, becoming colder and emptier. Others think it might one day stop growing and fall in on itself, called the Big Crunch. There's even the idea of a big rip, where the universe grows so fast that everything gets torn apart. Right now, we don't have a sure answer about how the universe will end. But the story of its beginning, from a tiny, hot and thick point to the giant space we see today, is one of the most amazing stories in science. The Big Bang Theory gives a wonderful explanation of how the universe came to be, starting from one tiny point. From that moment of great heat and thickness, the universe has been growing and changing, giving rise to stars, galaxies, and everything around us. Before atoms, before light, before even space and time as we know them, there was nothing. Or at least that's how we see it. But what does nothing really mean? In physics, nothing isn't truly empty. Instead, it's a strange, wild state, where tiny particles flicker in and out of being, where energy floats without shape, and where the rules of quantum physics are in control. So how did atoms, the very parts of matter, come out of this strange emptiness? To answer that, we must go back to the very start of everything, the birth of the universe. Our best scientific idea for how the universe began is the Big Bang Theory. It says the universe started as a tiny, hot and thick point, a place where all the energy and matter that would ever exist was packed together. Then, in a tiny moment, this point grew with great force, starting everything that followed. But if the universe came from one point, where did that point come from? And how could anything exist before time began? The answers lie in the strange world of quantum physics. In normal physics, nothing means empty space, total emptiness. But in quantum physics, nothing is never truly empty. Instead, it's full of tiny changes in energy that happen even in a vacuum. These changes can make short-lived particles that pop in and out of existence. But if a big enough change happens, it could cause something like the Big Bang, making a huge burst of energy that quickly grows into a universe. In other words, the universe might have come from one of these changes inside what seemed like empty space. When the universe suddenly appeared, it didn't have stars, planets, or atoms. It was a wild storm of energy, a hot and crazy mix where particles crashed into each other at extreme speeds. In these first moments, it was too hot for even simple atomic pieces to stay together. They just kept smashing and breaking apart. But as the universe grew, it cooled. And as it cooled, something amazing happened. Atoms began to form. As the universe cooled, energy turned into matter. This follows Einstein's famous rule which says energy and matter can change into each other. As energy dropped, tiny particles like protons, neutrons, and electrons started to appear. Protons and neutrons formed first, joining together in small groups thanks to the strong force, one of nature's four main forces. Electrons, which are much lighter, stayed apart at first, zooming around in the busy early universe. At this point, the universe was still too hot for full atoms to form. The strong energy kept breaking apart anything trying to stay together. About 3 minutes after the Big Bang, the universe had cooled enough for atoms' centers to form. This step, called nucleosynthesis, let protons and neutrons come together to form atomic centers. The first atoms were hydrogen and helium, the simplest elements. Hydrogen, made of just one proton and one electron, was the most common. Helium, with 2 protons and 2 neutrons, came next. A little lithium also formed. But their centers weren't enough. The universe was still too hot and electrons were being knocked away by strong light. This stopped atoms from fully forming. It took 380,000 years after the Big Bang for the universe to cool enough for full atoms to exist. This event, called the era of recombination, was a turning point. For the first time, electrons could settle around atomic centers without being knocked off by light. This meant stable hydrogen and helium atoms could finally form in big numbers. Once atoms formed, something amazing happened. The universe became clear. Before this, the universe was like a fog where light bounced everywhere. But once atoms formed, light could move freely. That light is still around us today as the cosmic microwave background, CMB, a faint glow scientists can see in every direction, showing us what the universe was like in the beginning. Even after atoms formed, the universe was still mostly empty and dark, filled with hydrogen and helium gas. But gravity was about to change everything. Over millions of years, small uneven spots in the gas caused some places to be thicker than others. These thicker spots pulled in more gas using gravity and got bigger. In time, the pressure and heat inside became strong enough to start nuclear fusion, the power source of stars. Inside the first stars, hydrogen atoms were squeezed together to make heavier elements, like carbon, oxygen, and iron. These elements, made inside stars, later became the parts for planets, life, and everything around us. Cosmic inflation is one of the most important ideas in modern science about the universe, as it helps explain the beginning of the universe and the patterns we see in it today. In simple terms, cosmic inflation is the idea that, in the very early moments after the Big Bang, the universe grew at an unbelievably fast rate, much faster than anything we could ever imagine. This time of fast growth played a key role in shaping the universe, deciding its structure, and setting the stage for everything that came after. But cosmic inflation didn't just happen on its own. It was the result of a careful balance of forces, each playing its part in creating the universe we now see. These forces, such as gravity, quantum mechanics, and the energy fields that existed in the early universe, work together in complicated ways, setting the base for galaxies, stars, planets, and even life itself. Before we talk about cosmic inflation, it's important to understand the Big Bang. The Big Bang wasn't an explosion in the usual way, but rather an event in which the universe began to grow from an extremely hot, packed, and tiny point. Everything in the universe was packed into this small space, and as it started to grow, the universe began its journey toward becoming the huge and complex thing we know today. However, there's a problem with the Big Bang idea when it's taken by itself. It doesn't explain why the universe is so even. If you look out into space, the universe seems mostly the same in all directions, with galaxies and stars spread in a pattern. But how did that evenness happen? Especially since the universe started out so wild and unstable. Cosmic inflation is an idea that was suggested in the early 1980s by scientist Alan Guth. It says that during the first few moments of the universe's life, it went through a time of very fast growth. This growth happened much faster than the speed of light. To put it simply, imagine something the size of a tiny grain of sand suddenly stretching to the size of the entire part of the universe we can see in just a very short moment. That's how fast the universe grew during this time. The idea behind cosmic inflation is that the universe began as a small, hot, and very packed point, but in just a tiny bit of time, the universe grew by a huge amount. This fast inflation helped smooth out any bumps and created the evenness we see in space today. It also explains why faraway galaxies are so far from each other, and why the universe looks the same in all directions. Now, let's talk about the forces that played a role in cosmic inflation. Several basic forces of nature work together to make this fast growth happen. These forces include gravity, quantum mechanics, and the energy field known as the inflaton field. Gravity, the force that pulls things toward each other, is one of the most well-known forces we see every day. It keeps us on the ground and makes things fall toward the Earth. But gravity also has a bigger job in the universe, especially during the early times of space. In the case of cosmic inflation, gravity helped shape how the universe grew. During inflation, the pulling force of gravity was not as strong compared to the energy made by the inflaton field. But after inflation ended, gravity became the main force in the universe, pulling matter together to form stars and galaxies. Quantum mechanics is the part of science that deals with the smallest things in the universe, things like atoms, electrons, and light particles. Unlike the usual behavior of objects we see every day, things at the quantum level act in weird and random ways. These tiny things exist in a state of chance, meaning they can be in many places or states at the same time. During cosmic inflation, quantum mechanics played a big role in the small changes that helped shape the big structure of the universe. Tiny quantum changes in the inflaton field caused small differences in how thick the universe was. These small changes grew over time, finally leading to the making of galaxies, groups of galaxies, and other things we see in space. The inflaton field is a guest field that is thought to have existed during the early universe. This field is believed to have caused the fast growth of the universe during the inflation time. In simple words, the inflaton field acted like a kind of energy that made space grow really fast. As the field worked with the universe's other forces, it gave the energy needed to make cosmic inflation happen. When the inflaton field lost its energy, the universe slowed down and started to grow at a much slower speed. This change from fast inflation to the slower growth we see today is called reheating, and it marked the start of the universe's current shape. After the inflation time ended, the universe was no longer growing at such a fast speed. But the effects of inflation were still very much there. The changes caused by the quantum field led to tiny differences in how much matter and energy there was, which later became the starting points for the making of galaxies, stars, and other space objects. These small differences caused matter to come together because of gravity. Over billions of years, this process led to the creation of stars, galaxies, and even bigger things like galaxy groups. The way matter is spread out in the universe today mostly comes from the patterns made by these small changes during the inflation time. One of the most amazing things about cosmic inflation is how different forces work together to make the universe as we know it. It wasn't just one force that made the universe grow fast. Instead, it was a mix of forces, gravity, quantum mechanics, and the inflaton field, that made the right conditions for inflation to happen. This careful balance of forces is a key part of why the universe has the shape and features it does. For example, if the force behind inflation had been too weak, the universe wouldn't have grown fast enough to smooth out the bumps we see today. But if inflation had been too strong, the universe could have grown too fast, stopping the creation of galaxies and stars. The forces that caused inflation also made the base for the making of the universe's big structure. By making tiny changes in the early universe, inflation gave the starting points for the cosmic web, the huge network of galaxies and galaxy groups that spread across the universe. These changes grew over time, leading to the galaxies and stars we see today. Cosmic inflation has deep effects on how we understand the universe. It suggests that the universe wasn't made from just one event, but from a very complicated and carefully balanced process that involved many forces working together. The universe's current structure, including the way galaxies are spread and the cosmic background glow, can all be traced back to this time of fast growth. Quarks are the smallest known bits in physics. Unlike atoms or molecules which we can see through microscopes, quarks are so tiny that they cannot be seen directly. Instead, scientists study them through powerful tests using particle smashers, which crash atoms together at very high speeds to show their inner parts. Quarks belong to a group of particles called basic particles. This means they are not made of anything smaller, at least based on what we know now in physics. Scientists believe that quarks are the main building blocks of protons and neutrons, which make up the centre of an atom. A key thing about quarks is that they never exist alone. Instead, they always come together to form bigger particles. This is because they are held together by a powerful force called the strong force, one of the 4 main forces of nature. Quarks come in 6 different kinds, or types. These types have strange names, but each has a role in shaping the universe. Up quark, down quark, charm quark, strange quark, top quark, and bottom quark. The up and down quarks are the most common because they form the protons and neutrons found in everyday atoms. The other 4 quarks, charm, strange, top, and bottom, are harder to find and are usually seen in very high energy places, like those made during particle crashes in labs or in the extreme conditions of the early universe. Each quark has a certain electric amount, which decides how it works with other particles. Up quarks have a charge of positive 2/3, while down quarks have a charge of negative 1/3. The mix of these charges is what gives protons and neutrons their total electric value. Atoms are made of 3 main parts: protons, positive particles, neutrons, particles with no charge, and electrons, negative particles that go around the centre. Quarks are in charge of making the first 2, protons and neutrons, which sit in the middle of an atom, known as the nucleus. Each proton is made of 2 up quarks and 1 down quark. Each neutron is made of 2 down quarks and 1 up quark. These quarks are held together by another type of particle called a gluon. Gluons act like an invisible force that sticks quarks together, making sure that protons and neutrons stay whole. This force is incredibly strong, much stronger than gravity or magnetism, which is why protons and neutrons stay tightly packed inside the middle of an atom. Electrons, on the other hand, are not made of quarks. Instead, they belong to a separate group of particles called leptons. Even though they're different, electrons are very important in atoms by circling the center, making the shape that allows atoms to link and form groups of atoms or molecules. The story of quarks begins at the very start of the universe, during the Big Bang, which happened about 13,800,000,000 years ago. At the moment of the Big Bang, the universe was an unbelievably hot and crowded sea of energy. In the first tiny part of a second, the energy cooled enough to let quarks form. These quarks existed freely for just a short moment before the strong force pulled them together to form the first protons and neutrons. As the universe kept growing and cooling over the next few minutes, these protons and neutrons came together to form the first atomic centers. But it took another 380,000 years before the universe cooled enough for electrons to join them, forming the first full atoms, mostly hydrogen and helium. Over billions of years, these atoms joined together to form stars, planets, and finally, everything we see today. For many years, scientists thought that protons and neutrons were the smallest pieces of matter. But in the 1960s, scientists Murray Gell-Mann and George Zweig said that these particles were actually made of even smaller parts, what we now call quarks. Their idea was later proved through high-energy tests in particle smashers, which broke apart protons and neutrons and showed what's inside. Today, scientists still study quarks using very advanced machines like the Large Hadron Collider, the most powerful particle smasher in the world. One of the most exciting finds happened in 1995, when scientists at the Fermilab lab finally found the top quark, the last missing part of the quark family. Quarks are not just tiny pieces hidden in atoms, they are the very base of all matter. Quarks also help us understand nuclear energy, which powers the sun and gives us electricity through nuclear power plants. Also, studying quarks has led to big discoveries in healthcare, technology, and space research. Quarks can never be alone. Unlike electrons, which can move around by themselves, quarks always stay in groups. This happens because of a special rule called confinement. Quarks have color charges. Even though they're too small to have real colors, scientists use color names like red, green, and blue to help explain how they work. The top quark is very heavy. In fact, it's about as heavy as a gold atom, even though it's much smaller than a proton. Quarks exist in unusual particles. While protons and neutrons are the most common particles made of quarks, scientists have found others, like pions, kaons, and tetraquarks, which act in odd and surprising ways. Gluons act as the glue that holds quarks together. They're in charge of carrying the strong force, one of the 4 main forces of nature. Without gluons, quarks couldn't form protons or neutrons, which means atoms, and everything made of atoms, wouldn't exist. Right after the Big Bang, the universe was extremely hot and packed. Scientists think that in the first small part of a second, less than a trillionth of a second, the whole universe was a boiling mix of quarks and gluons called quark-gluon plasma. This state of matter was nothing like what we know today. The heat was over 1 trillion degrees Celsius, hotter than the core of any star. At such high temperatures, quarks and gluons were free. They didn't form protons, neutrons, or any other stable particles. Instead, they kept crashing into each other, coming together and breaking apart in a fast and powerful way. As the temperature dropped below a certain level, around a few trillion degrees, quarks and gluons started to stick together. This process is called hadronization. During hadronization, quarks joined in specific ways to form bigger particles called hadrons. The most important hadrons for the growth of the universe were protons, made of 2 up quarks and 1 down quark, neutrons made of 2 down quarks and 1 up quark. This step in the universe's growth was very important. Without it, the basic parts needed for atoms would never have come together. The crashes between quarks and gluons at that time were full of energy, shaping how matter appeared. The strong force carried by gluons made sure quarks stuck tightly together. Even as the universe kept growing and cooling, the bonds between quarks stayed strong, leading to the forming of atomic centers. One of the most important forces during these early events was the strong force. Unlike gravity, which pulls things together from far away, or electromagnetism, which affects charged particles, the strong force only works over very tiny distances, inside atomic centers. The strong force carried by gluons is so strong that it stops quarks from ever being alone. That's why we never see free quarks in nature. They're always found in bigger particles like protons and neutrons. Think of gluons like an invisible rope that pulls quarks together, like a strong magnet sticking metal pieces together. The difference is, the strong force is way stronger than magnetism, so strong it even beats the push between protons in an atomic center. Once quarks and gluons had formed protons and neutrons, the universe kept growing and cooling. This let protons and neutrons come together through nuclear fusion, making the first atomic centers. At this point, the universe was still a hot, thick mix of charged particles, meaning electrons hadn't yet formed orbits around centers. But as it got cooler, electrons were finally able to join the centers, creating the first full atoms. This process, called recombination, happened around 380,000 years after the Big Bang and marked the start of the universe as we know it. With atoms now formed, light could finally move freely for the first time. This event caused the cosmic microwave background, which scientists can still see today as a soft glow across the universe. Learning how quarks and gluons acted in the early universe isn't just an idea on paper. Scientists have been able to copy the same conditions as quark-gluon plasma in big particle smashers, like the Large Hadron Collider in Switzerland and the relativistic Heavy Ion Collider in the United States. By crashing heavy atoms like gold or lead at almost light speed, scientists can make heat high enough to briefly make quark-gluon plasma. These tests help researchers learn how quarks and gluons behave, giving them deeper knowledge of the universe's first moments. Thanks to these tests, scientists have found that quark-gluon plasma acts like a nearly perfect liquid, meaning it flows with almost no resistance. This finding has helped improve what we know about the forces that shape the universe. The crashes and actions of quarks and gluons in the early universe played a major part in shaping everything we see today. If these tiny bits hadn't come together just right, the universe would be totally different. There would be no protons, neutrons, or atoms, meaning no stars, no planets, and no life. By studying quarks and gluons, scientists learn more about the true nature of matter. These particles, which once floated freely in the wild heat of the early universe, are now locked inside the stable matter that makes up everything. Quark confinement is a strange rule of nature. No one has ever seen a quark by itself. Unlike electrons, which can be alone, quarks are always found in groups. They come in threes to make protons and neutrons, or in pairs to form particles called mesons. This happens because of a force so strong that trying to pull quarks apart just makes them stick together harder. This force is the strong nuclear force, and it's the strongest force in nature, much stronger than gravity or magnetism. To understand this, picture two quarks joined by a rubber band. If you try to pull them apart, the rubber band stretches and stores energy. But instead of snapping, the energy turns into new quarks and antiquarks, which instantly form new particles. That's why quarks are never alone. They're always stuck inside bigger particles. Billions of years ago, right after the Big Bang, the universe was extremely hot and full of energy. During that time, quarks moved freely, like water in steam. But as the universe grew and cooled, quarks started to stick together, held by the strong force. At first, they formed groups of three, making protons and neutrons. Protons are made of 2 up quarks and 1 down quark, while neutrons have 2 down quarks and 1 up quark. The force holding these quarks together is so strong that nothing in nature can pull them apart. This was the start of the particles that would later form atomic centers, the heart of every atom in the universe. Without quark confinement, there would be no protons or neutrons, and without them, atoms would never have formed. That means no elements, no molecules, and no life. The strong force that traps quarks inside protons and neutrons also works on a bigger scale, holding protons and neutrons together inside atomic centers. Without it, atomic centers would fly apart because of the push between positive protons. This force, carried by gluons, acts like an invisible rope, making sure protons and neutrons stay packed together. Scientists have spent many years trying to fully understand quark confinement. The theory that explains it is called quantum chromodynamics, QCD. According to QCD, quarks carry a kind of color charge, much like electric charge, but instead of positive and negative, there are three kinds: red, green, and blue. The strong force makes sure that quarks always join in a way that their colors cancel out, keeping them forever trapped. When we think about the beginning of the universe, the question that often comes to mind is, what was there before anything existed? How did everything come into being from what seems like nothing? This question has confused scientists, philosophers, and thinkers for hundreds of years, and it touches on one of the deepest mysteries of existence. At the center of this puzzle is the idea of nothingness, a void, an emptiness, a space with nothing in it that existed long before atoms, stars, and galaxies came to be. But the story of this nothingness is far more complicated and interesting than we might first think. This nothingness is not just an absence of matter, it is a strange state that has the power to create everything we know. Before jumping into the puzzles around nothingness, it's important to understand what we mean by the word nothing. In our daily lives, nothing seems like an easy idea to understand. If you have an empty room, you might think there is nothing in it. But even in that case, the room has air, light, and the chance to hold something else. The nothing that space scientists talk about is not this simple emptiness. Instead, it is a state with no matter, no energy, and not even space itself. It's a true empty place, a state of complete nothingness. Now let's imagine a time before the universe was born. There were no stars, no planets, no atoms, and not even the space we know today. In fact, the very idea of space didn't exist in the way we understand it. It was a time before the Big Bang, a time when the rules of physics as we know them didn't work in the same way. At this point, everything we think of as something had not yet been created. So, what was this nothingness like? Was it really empty, or was there something more gentle and strange happening in that space? According to modern science, this emptiness wasn't as still as it may seem. In fact, this empty space may have been the starting point of all the matter, energy, and forces that make up our universe today. The question of how something can come from nothing is often called a puzzle. If there was nothing, how could anything possibly begin to exist? It seems to go against all logic and common sense. But modern science, especially quantum physics, gives a surprising answer. In the world of quantum physics, nothing is not truly empty. Even in a vacuum, there is a strange and puzzling action taking place. This action is called quantum fluctuations. Quantum fluctuations are tiny, random changes in the energy of empty space. These changes are brief, quick bursts of energy that can suddenly appear from nothing and then disappear. While these energy changes are incredibly small and short-lived, they are real and can be measured. These changes show that even in a true vacuum, where no particles are found, there is still a kind of action happening on the smaller scales. This is not something we can see with our eyes, but it is something we can detect and understand through the rules of quantum physics. Now, let's return to how the universe began. The Big Bang, which is believed to have happened about 13.8 billion years ago, was not an explosion in space. It was the spreading out of space itself. At the very start, all the energy and matter that would later become the universe were packed into an incredibly hot, dense point known as a singularity. But how did this singularity come to be? And how did it come from nothing? Some scientists believe that the energy changes in the quantum vacuum could have started the Big Bang. In simple terms, the empty space chose to shake things up and create particles, energy, and later the whole universe. This process is called quantum creation. It suggests that space itself can change, and in the right conditions, these changes could lead to the creation of matter and energy. In this way, the rules of physics that control how particles and energy behave in our universe could have come from the very nothingness that existed before. This idea leads to an exciting possibility. maybe the entire universe, everything we see around us from the smallest bits to the largest galaxies, was born out of a quantum change in the vacuum of nothingness. In this way of thinking, the creation of the universe wasn't a single event, but rather the ongoing result of these changes in the fabric of space and time. So, if the universe came from nothing, how do the laws of physics fit in? How is it possible for the universe to follow set rules if it was created from a space where no rules existed? This question challenges how we understand the universe, but it is here that the beauty of science becomes clear. One important idea to understand is that the rules of physics are not random, they come from the basic features of the universe. When we talk about the laws of physics, we're talking about the rules that control how matter and energy behave. These rules include gravity, the way subatomic particles interact, and the rules of heat and energy. But where did these rules come from? How did they come out of nothing? According to current science, the rules of physics might not have been set the way they are now at the time of the Big Bang. In the very early moments of the universe, right after the Big Bang, the rules of physics may have been very different. For example, it is believed that the universe went through a period of superfast expansion called inflation. During this time, space itself grew at a huge rate, and the basic forces that control the universe, gravity, electricity and magnetism, and the strong and weak nuclear forces, might not have been separate. In the very high-energy world of the early universe, these forces may have been one single force, a superforce, that later split apart as the universe cooled. The idea that the rules of physics could change over time is a hard one to imagine, but it is supported by what scientists observe and the math they use. As the universe cooled and grew, the conditions changed, and the forces that control matter started to take on the forms we see today. It's like the universe began with a few very simple, basic rules that slowly turned into the complex set of rules that control everything we see now. In this way, the universe may have grown from the simplest beginning, a quantum change in empty space, into the highly organized system we now see. The rules of physics that we assume are always there were not placed from outside the universe. Instead, they are built into the very fabric of space and time, coming naturally from the conditions that appeared after the Big Bang. The quantum vacuum, often called empty space, is not as empty as it might look. It is, in fact, full of possibility. At the most basic level, space is filled with quantum fields that stretch across the whole universe. These fields are the base of matter and energy, and they are the reason for the creation of particles, the spreading of forces, and even the very shape of space and time. Even when no matter or energy is present, these quantum fields are still doing something. They interact with each other, moving and changing with energy, even when no visible particles are there. This activity is what leads to the strange happenings of quantum physics, like pairs of particles and antiparticles that suddenly appear and vanish in a flash. The idea of a quantum vacuum also goes against our old way of thinking about empty space. In older science, empty space was thought to be a total nothing, but in the quantum world, empty space is not empty at all. It is a lively, ever-changing field full of energy and chances. In a way, the quantum vacuum is the starting point of everything. It holds within it the possibility for all the particles, forces, and shapes that make up our universe. The vacuum is not just a quiet emptiness. It is a field of creation, where anything can possibly come into being from the energy changes and interactions of quantum fields. Everything around us, the air we breathe, the ground under our feet, the stars in the night sky, was once made in the heart of the universe through an amazing process called nucleosynthesis. This is the way by which atoms are made, starting from the very beginning of the universe and continuing inside stars, during huge space explosions, and even in deep space. Imagine the universe at the very start, a hot, thick, and wild place. This was the time of the Big Bang, an event that began everything. In the first few minutes after the Big Bang, temperatures were extremely high, and tiny bits called nucleons, protons and neutrons, were moving around very fast, constantly crashing into each other and joining together. During this short but very important time, called Big Bang nucleosynthesis, the first atomic centers were made. But since the universe was growing fast, it cooled down quickly. After about 20 minutes, it became too cold for more nuclear changes to happen. By then, almost all the matter in the universe was in the form of hydrogen and helium, the two lightest and most common elements. A tiny bit of lithium and deuterium, a heavier kind of hydrogen, also formed. This means that at the start of time, the universe was mostly a huge sea of hydrogen and helium, with only small traces of other elements. So where did all the other elements, like oxygen, carbon, gold and iron, come from? The answer is in the life and death of stars. Stars are not just bright lights in the sky, they are huge natural nuclear machines that make new elements deep inside their hot centres. This process is called stellar nucleosynthesis. A star forms when a large cloud of hydrogen gas gets pulled together by gravity, starting nuclear fusion in its centre. This fusion process smashes hydrogen atoms together, making helium and giving off huge amounts of energy. This is what makes stars shine. As stars get older and hotter, they start turning helium into heavier elements like carbon, oxygen, neon and silicon. In the biggest stars, this keeps going until iron and nickel are made. But something important happens here. Once a star makes iron, fusion stops giving off energy. Instead, the star becomes unstable, and in the biggest stars this causes one of the most amazing events in space, a supernova explosion. A supernova is a huge star explosion that happens when a large star reaches the end of its life. During this explosion, the star throws out all the elements it made into space, adding to the mix of heavier elements in the universe. But that's not all. Supernovae also make new elements through strong nuclear reactions. In the split-second mess of the explosion, atomic centres crash together in ways that don't happen inside a normal star. This makes even heavier elements, like gold, uranium, and platinum. There's another special process that happens here, called the R process, fast neutron capture process. This happens when atoms take in lots of neutrons very quickly, letting them grow into much heavier elements. Supernovae are one of the main places where this happens. Recent studies have found another space event that makes heavy elements, neutron star collisions. Neutron stars are the super-dense leftovers of big stars that exploded. When two neutron stars spin toward each other and crash, a huge amount of energy is released, along with lots of material full of neutrons. This kind of place is perfect for the R process, which means neutron star crashes are a big source of some of the rarest and heaviest elements in the universe, like gold, platinum and rare earth metals. In fact, the gold in your jewellery and the uranium in power plants may have come from one of these space crashes billions of years ago. Not all elements are made inside stars or in explosions. Some are made in a completely different way called cosmic ray spallation. Cosmic rays are fast-moving particles always flying through space at almost the speed of light. When they hit atoms floating in space, they break them into smaller parts, making new, lighter elements. This is how rare elements like beryllium and boron are formed. Cosmic ray spallation doesn't just happen in deep space, it also happens in our own solar system, on asteroids, meteoroids, and even in Earth's air. Some of the rare versions of elements found on Earth, called cosmogenic nuclides, come from this process. Even though most of the universe's elements were made in stars, Earth still makes new atomic centres through radioactive decay. This is a slow process where unstable atoms, called radioisotopes, slowly break down into lighter elements over time. For example, uranium, thorium, and potassium-40, which have existed since Earth was formed, continue to break down, giving off radiation and turning into other elements. This helps create some of the heat inside our planet, which drives volcanoes and moving land plates. Every element in your body, every metal in your phone, every drop of water in the ocean came from the universe's nuclear factories, the Big Bang, the hearts of stars, exploding supernovae, neutron star crashes and cosmic rays. The universe is really a huge recycling machine, always forming, breaking and reshaping elements over billions of years. Even now, new stars are being born from the remains of older ones, keeping the cycle of element making going. And maybe, billions of years from now, atoms from our sun will be part of new planets, new life, or even another smart civilization looking at the stars, wondering where it all began. Only a few minutes after the Big Bang, the universe had cooled enough for these protons and neutrons to start sticking together, making the first atomic centers. This process, called Big Bang nucleosynthesis, made some of the lightest elements: hydrogen, helium, lithium, and beryllium. These were the only elements made in large amounts during this early time because the conditions weren't right to make heavier elements like carbon or oxygen. One main reason for this limit was time. The universe was growing fast, causing temperatures and pressure to drop. The process of fusion, where atomic centers join to make heavier elements, needs both high temperatures and strong pressure to keep going. But as the universe expanded, it cooled down too fast for more element making, stopping nuclear reactions after about 20 minutes. While the Big Bang gave the universe its first set of elements, it was stars that became the factories for making heavier ones. The first stars formed around 500 million years after the Big Bang, using the hydrogen and helium left over from the universe's birth as their fuel. Inside these stars, under huge heat and pressure, nuclear fusion happened. This process turned hydrogen atoms into helium, and later, as the stars aged, turned helium into heavier elements like carbon, oxygen, and nitrogen. This is where carbon, the element needed for life, finally came to be, something that couldn't happen during the Big Bang itself. But not all stars could make elements heavier than carbon. It took the violent ends of big stars, supernovae, to make elements like iron, gold, and uranium. When a star exploded in a supernova, it gave off a huge burst of energy, allowing for fast fusion of elements heavier than iron. Interestingly, some of the light elements like lithium, beryllium, and boron weren't just made in the Big Bang, but also later by cosmic rays. Cosmic rays are fast-moving particles, mostly protons, that fly through space nearly at the speed of light. When they hit atoms and gas and dust between stars, they break apart heavier elements into smaller pieces, a process called cosmic ray spallation. This means that even billions of years after the Big Bang, these lighter elements kept forming in space. The making of elements heavier than iron needed even more extreme conditions than those inside normal stars. Some of these heavy elements, like gold, platinum, and uranium, were made in the crashes of neutron stars, the super-dense leftovers of big stars. When two neutron stars crash, they make powerful bursts of energy, starting nuclear reactions that create some of the rarest elements in the universe. Also, on Earth, some elements like argon-40 were made through radioactive decay, a natural process where unstable atoms break apart over time, changing into other elements. Over billions of years, Earth's makeup has been shaped by a mix of nuclear reactions in space, cosmic rays, and changes inside the Earth. The study of how elements form, called nuclear astrophysics, is still a major area of science. Scientists study stars, supernovae, and neutron star crashes to better understand how different elements were made. Even though the Big Bang began the making of elements, the story of nucleosynthesis has been going on for billions of years, shaping everything we see around us today, from the air we breathe to the gold in our rings and the carbon in our bodies. The elements that make up everything in the universe, from faraway galaxies to our own DNA, started in the hot birth of the universe, grew inside old stars, and were spread across space by huge explosions and fast-moving particles. The universe is, in a way, a giant space lab where nature has been making the ingredients of life for billions of years. At the start of human science, the origin of elements was a total mystery. Early ideas said that all the elements were made at the very beginning of the universe. But scientists couldn't find a clear way for that to happen. As they kept studying, they found that the most common elements in the universe were hydrogen and helium. Together, they made up almost all the known matter in space, while other elements, like oxygen, carbon, and iron, made up less than 2% of the total mass of the solar system and other star systems. At the same time, scientists noticed something interesting. Oxygen and carbon were the next most common elements after hydrogen and helium. They also saw a pattern: lighter elements, especially those made up of whole numbers of helium-4 centers, also called alpha particles, were more common than others. But where did all these elements come from? In 1920, British space scientist Arthur Stanley Eddington had a bold idea. He said that stars make their huge energy by joining hydrogen atoms together to make helium. Not only that, but he also said that stars could be the ones making heavier elements. But at that time, scientists didn't yet understand how nuclear fusion worked, so Eddington's idea wasn't widely accepted. Still, His idea became the base for later discoveries. Just before World War II, German-American scientist Hans Bethe figured out the exact nuclear steps that power stars. He explained how hydrogen atoms join under extreme heat and pressure inside stars to make helium, a process that gives off a huge amount of energy. This process, called nuclear fusion, is what keeps stars shining for billions of years. After World War II, British scientist Fred Hoyle built on Bethe's work. He tackled an even bigger question. How do stars make heavier elements like carbon, oxygen, and iron? Hoyle's research led him to a major discovery. He suggested that all the elements in the universe beyond hydrogen and helium were made inside stars. As stars got older and went through different stages of their lives, they acted like giant space furnaces, joining lighter elements into heavier ones. When these stars finally exploded in supernovae, they spread the newly made elements into space, filling the universe with the basic parts needed for planets and life. But Hoyle had another bold idea. He said that hydrogen itself was always being made from the emptiness of space. He thought that the universe didn't have a single beginning, but was always being created. This idea was part of what he called the steady-state theory, which went against the idea of one single creation event, like the Big Bang theory. The idea that the universe had a beginning was actually shared much earlier. In 1931, Georges Lemaitre, a Belgian scientist and priest, said the universe began from a single, incredibly packed point he called the primeval atom. Over time, this point grew, creating all the matter and space we see today. Interestingly, it was Hoyle himself who came up with the name Big Bang in a 1949 BBC radio broadcast. He used the phrase to explain Lemaitre's idea in contrast to his own steady-state theory. Many people think Hoyle meant it as a joke, but he later said he was just trying to make the idea easier to picture. Even though Hoyle strongly disagreed with the Big Bang theory, both ideas helped explain how elements were made. The Big Bang theory explained why there was so much hydrogen and helium in the universe, as well as why some light elements like deuterium and lithium existed. On the other hand, Hoyle's work on making elements in stars explained how heavier elements were made inside stars. In the 1950s and 1960s, Hoyle's ideas were expanded by other scientists, including William A. Fowler, Alistair G. W. Cameron, and Donald D. Clayton. Their work helped form a clearer picture of how stars change and create different elements. One of the most important papers in this area was published in 1957 by E. Margaret Burbidge, Jeffrey R. Burbidge, William A. Fowler, and Fred Hoyle. This paper, often called the B2FH paper after the author's initials, became a key piece of modern space science. It described the different nuclear steps that happen inside stars, turning one element into another. At the same time, scientists were also looking at how much of each element was found in space rocks. Hans Suess and Harold Urey made a table showing how the different elements were spread across the universe. When they graphed the amounts of each element, the pattern looked like a jagged saw blade, meaning some elements were much more common than others. This strange pattern gave important clues about how elements formed in different places, from the hot centers of stars to the powerful blasts of supernova. Today, scientists know that different types of stars make different elements depending on how big they are and what stage of life they're in. Small stars, like the Sun. These stars mostly turn hydrogen into helium over billions of years. When the hydrogen runs out, they grow into red giants and start turning helium into carbon and oxygen. Big stars. These stars use their fuel much faster. As they age, they go through a series of fusion steps, making heavier and heavier elements. They can form neon, magnesium, silicon, and even iron. Supernovae. When a big star reaches the end of its life, it explodes in a supernova. This explosion is so strong that it makes even heavier elements like gold, silver, and uranium. These elements are then thrown into space, later becoming part of new stars, planets, and even living things. Neutron star collisions. Recent findings show that when two neutron stars crash into each other, they make a huge amount of rare, heavy elements like gold and platinum. This step, called the R process, helps explain why these elements are found on Earth. Learning about nucleosynthesis isn't just about where elements come from. It helps us learn the story of the universe itself. The elements that make up our bodies, our planet, and everything we see were created in the hearts of old stars billions of years ago. Every atom of oxygen we breathe, every carbon atom in our bodies, and every drop of water we drink has a space origin. The study of nucleosynthesis keeps growing, with new findings showing more about the steps that shape the universe. By studying faraway stars, supernovae, and neutron star crashes, scientists keep learning more about how elements formed and how the universe keeps changing. In the big picture, we're all made of star stuff, bits of ancient stars that lived and died long before our solar system was born, and that maybe is the most amazing story of all. The process of nucleosynthesis, the making of elements in space, is an amazing and important part of how the universe works. It is how elements form, from hydrogen and helium to some of the heaviest elements we see in the periodic table today. These steps mostly happen in stars, which are like space factories where elements are made. The way stars do this is a chain of nuclear reactions called stellar nucleosynthesis. Learning about this helps us see inside stars and understand how the elements around us came to be. At the center of every star is nuclear fusion, a process that powers the star and makes the elements found in the universe. These reactions start with hydrogen atoms, which are the simplest and most common element in the universe. In stars, hydrogen atoms combine to form helium through a set of reactions. This is called hydrogen burning. There are two main ways this happens: the proton-proton chain and the CNO cycle. In the proton-proton chain, hydrogen atoms, protons, crash into each other and join to form helium-4, giving off energy as light and heat. This is the main process in smaller stars like our Sun. The CNO cycle is more important in bigger stars. It also joins hydrogen into helium but uses carbon, nitrogen and oxygen to help push the reaction. After a star uses up the hydrogen in its core, it starts to burn helium. This is called helium burning, where helium atoms join together to make heavier elements like carbon and oxygen. As the star gets older and the core gets hotter and more squeezed, it can start to burn even heavier elements. This chain of burning continues through carbon burning, neon burning, oxygen burning and silicon burning. These steps make elements all the way up to iron and nickel. Iron is special in nucleosynthesis because it has the most tightly packed atomic core. This means that trying to fuse iron doesn't release energy, it actually takes energy. That's why stars stop making energy when they reach iron. But how are elements heavier than iron, like gold and uranium, made? These can't form the same way as lighter ones. Instead, they are made through a step called neutron capture. In stars, especially in extreme places, atoms can grab neutrons, leading to the making of heavier elements. This happens in two main ways, the S process and the R process. The S process, or slow neutron capture, happens in stars in their later life stages. It works when atoms slowly take in neutrons and become heavier. These heavier elements are released into space when the star dies and explodes or sheds its outer layers. These elements mix into space, adding to the material that forms new stars, planets, and life. The R process, or rapid neutron capture, happens in more violent places, like during supernova or neutron star crashes. In these events, neutrons are grabbed so quickly that very heavy elements form in seconds. The R process makes many of the heaviest elements in the universe, including gold and uranium. Supernovae, the huge explosions of massive stars at the end of their lives, are one of the main places where nucleosynthesis happens. A supernova releases a huge amount of energy and matter into space. When a massive star dies, it can no longer fuse elements in its core. It collapses, and the explosion blows off the outer layers of the star. The extreme heat and pressure allow for the creation of heavy elements like gold, platinum and uranium through the R process. Neutron star collisions are also now seen as a big source of heavy elements. When two neutron stars smash into each other, they release a huge burst of energy and throw large amounts of heavy elements into space. These events are also thought to make gold and platinum, adding to the universe's store of heavy elements. Before stars formed, there was the Big Bang. In the first moments of the universe, temperatures and pressures were so high that nuclear fusion happened freely. This time, called Big Bang nucleosynthesis, happened in the first 3 minutes of the universe's life. During this time, the universe was still very hot and thick, filled with glowing particles. As it cooled, protons and neutrons formed, and nuclear reactions began. During Big Bang nucleosynthesis, a few light elements were made. These included hydrogen, the most common element, helium, the second most common, and small amounts of lithium and beryllium. The whole process lasted only about 20 minutes. After that, the universe became too cool and spread out for nucleosynthesis to go on. By the end of this time, most matter was in the form of hydrogen and helium, with small traces of lithium and beryllium. One important thing we learn from Big Bang nucleosynthesis is that the light elements made during this time make up most of the universe's mass. For example, almost all the helium in the universe was made in the Big Bang and is still being made in stars today. The steps of nucleosynthesis, whether in the early universe, inside stars, or in supernovae and neutron star crashes, have shaped the universe and everything in it. They created the elements that make up stars, planets, and life. Without nucleosynthesis, we wouldn't have elements like carbon, oxygen, and iron. By studying nucleosynthesis, scientists can learn more about how the universe changed over time. The patterns of elements in stars and galaxies tell us how those stars formed and what happened in their cores. It also helps us understand where life's key elements, like carbon and oxygen, came from, and how they were spread across space. Stellar nucleosynthesis is how stars make new elements. It happens inside stars during their life, and it makes elements like carbon, oxygen, and iron. Stars are like giant furnaces, where lighter elements like hydrogen and helium are joined into heavier ones. As stars age and their cores get hotter, this fusion process becomes more complex, making more and more heavy elements. One of the key elements made in this process is carbon, which forms through a special step called the triple alpha process. It's an important step that allows even heavier elements to form. Carbon also helps release free neutrons in stars. These neutrons then help with the S process, where iron atoms absorb neutrons and turn into heavier elements like gold and uranium. After stars make these elements, they don't keep them. The elements are sent into space when stars lose mass, either through soft winds in smaller stars or huge explosions in big stars. These blasts throw the new elements into space, adding to the gas and dust that will form new stars and planets. The first clear proof that stars make heavy elements came when scientists saw that the gas between stars became richer in these elements over time. Stars that formed later in the galaxy had more heavy elements than older stars. In 1952, scientists found technetium, a short-lived radioactive element, in the air of a red giant star. This was big news because technetium breaks down quickly, meaning it had to be made recently in that star. This showed that nuclear reactions were happening inside stars. More proof came from seeing elements like barium in stars. Stars in the late phase of their life, called the asymptotic giant branch, had much more barium than younger stars. This confirmed that the S process was at work inside these stars, making heavier elements. One of the most exciting signs that show stars create elements comes from something called stardust, or presolar grains. These tiny solid pieces which formed from the gases around stars are often found in space rocks called meteorites. By studying their isotopic makeup, that is, the kinds of atoms they hold, scientists can learn a lot about the chemical changes that happened inside stars before they died. These grains give us a clear view into the life of stars and offer important clues about how stars make the elements we see in the universe today. Supernovae, those incredibly powerful star explosions, are more than just amazing space events. They are some of the main places in the universe where heavy elements are made. These elements are a key part of the matter in the universe. The way elements are formed during a supernova is called supernova nucleosynthesis. This happens in the superhot and high-pressure setting of a supernova, where nuclear reactions take place very quickly. During these reactions, elements between silicon and nickel are made. When a star explodes in a supernova, the energy is so strong that atoms smash together quickly. These reactions allow atoms to join and make new, heavier elements. The process mostly creates elements with atomic numbers between silicon, which has 14 protons, and nickel, which has 28 protons. These elements are made through a process called quasi-equilibrium. Quasi-equilibrium is a state that is almost balanced. This means the nuclear reactions are nearly in balance but not fully. A special imbalance is caused by the large number of silicon atoms in the mix. This imbalance creates a special set of nuclear conditions that make it possible for elements to form in the core of a supernova. The idea of quasi-equilibrium was a major step forward in the study of how elements are made in stars. Before this, scientists thought that a different process called the alpha process was responsible for forming these middle elements in supernovae. This alpha process, described in the 1957 B2FH paper, named after the writers Burbage, Fowler and Hoyle, involved adding helium atoms again and again to lighter elements to make heavier ones. But the idea of quasi-equilibrium turned out to be more correct and replaced the older alpha process. Besides the process that makes elements from silicon to nickel, another very important method in supernova is the R process, or rapid neutron capture process. The R process creates some of the heaviest elements in the periodic table, elements like uranium and thorium, which are key parts of the natural radiation found in space. The R process happens when an atomic nucleus quickly captures neutrons and then changes into something new. What makes the R process special is that it happens so fast that the neutrons don't have time to break apart. This quick neutron capturing builds heavier and heavier atoms. The free neutrons are made during the collapse of a supernova's core, especially through something called electron capture, where electrons are taken in by protons and changed into neutrons. This is one of the main ways the free neutrons needed for the R process are made. Interestingly, the R process doesn't depend on which elements were in the star before it exploded. Even if the star was mostly made of hydrogen and helium, the two lightest and simplest elements, the R process can still happen. That's because the R process depends on the large number of free neutrons in the star's collapsing core, not on what the star was made of before. Astronomers have found strong proof that the R process is indeed how many of the heaviest elements were made. For example, when scientists looked at very old stars with fewer heavy elements, they still saw that those stars had many R process elements. This shows that these elements were made early in the universe, long before the stars we see today were even formed. The R process is important not just for making heavy elements, but also for creating the versions of elements with the most neutrons, called isotopes. These help scientists understand the full mix of elements in the universe. Still, even though there has been a lot of progress, scientists don't fully understand how the R process works in supernovae, and getting accurate numbers for R process elements is still hard. Another process in the making of elements is the RP process, or rapid proton capture process. This process is like the R process, but instead of neutrons, it quickly adds protons to atoms to make heavier ones. However, unlike the R process is not yet fully proven. Some scientists think it helps create lighter, proton-rich elements, but its exact role in element making during supernovae is still being studied. It may be important in certain kinds of stars, but more research is needed to know for sure. When a supernova explodes, it lets out an enormous amount of energy. The explosion happens so fast that radioactive decay, the process where unstable atoms break down, doesn't have time to change things much. This means that the supernova process can make elements with equal numbers of protons and neutrons. These are stable and very common. One major step in this process is the joining of oxygen and silicon atoms at very high temperatures. This makes new, heavier atoms up to nickel. The final elements include many forms of titanium, chromium, iron, and nickel. For instance, an atom like nickel-56, with equal numbers of protons and neutrons, is very stable up to a point. But not all the atoms made in this way are stable. Some are radioactive and break down over time into other elements. For example, radioactive forms like titanium-44, chromium-48, iron-52, and nickel-56 are made in large amounts during a supernova explosion. Over time, they turn into stable forms like titanium-48, chromium-52, and iron-56. One exciting part of supernova element making is the production of gamma rays. These are very strong light particles given off during the decay of radioactive atoms. These gamma rays can be seen with space tools and help scientists study what happens in a supernova explosion. Finding these gamma rays was one of the most important steps in the field of gamma ray astronomy. In the year 1987, astronomers saw a supernova explosion called Supernova 1987A. This event gave one of the best pieces of proof for explosive element making. Gamma-ray signals were seen coming from the explosion, and they showed the presence of isotopes like cobalt-56 and cobalt-57. These were formed as the radioactive cobalt atoms broke down, and because they only last about a year, it proved they were made during the explosion. These gamma rays weren't a surprise. Scientists had predicted in 1969 that they would be a key way to prove how elements are made in supernovae. This idea was important in planning NASA's Compton Gamma Ray Observatory, which was built to see these rays. Besides the gamma rays, more proof of element making in supernovae comes from tiny bits of stardust. These are microscopic particles that form as the supernova cools and spreads out. As they cool down, they trap certain atom types, which scientists can study to learn more about what happened during the explosion. One amazing discovery is the high amount of titanium-44 in these grains. This matched predictions made in the 1970s about these special stardust grains, now called pre-solar grains. They give a clear look into the chemical steps that happened in a star before it exploded. The crashing together of two neutron stars, called binary neutron star (BNS) mergers, has recently been found to be a major way that some of the heaviest elements are made. Neutron stars are very dense leftovers from big stars. Scientists thought that when two of them crashed into each other, they could make heavy elements. This idea was confirmed in the year 2017. That year, groups like LIGO, Virgo, and the Fermi Gamma Ray Space Telescope saw both gravitational waves and light from a neutron star crash called GW 170817. This was the first direct proof of such a crash, and showed that elements like gold were made in the remains of the collision. These heavy elements formed as the tightly packed matter cooled and broke down after the event. This discovery helped scientists learn how heavy elements are created. While we now know that neutron star crashes make many of these elements, another big event happened in the year 2021. That year, scientists saw the first collision between a neutron star and a black hole. Still, most research shows that two neutron stars crashing is the main way these metals are made. Ongoing studies of these huge space events are helping scientists understand how the elements that make up our world came to be. Element making, called nucleosynthesis, also happens in the disks of matter around black holes. These are spinning rings of material being pulled in by a black hole's strong gravity. As this material heats up, it can make new elements. Another interesting process in the universe is cosmic ray spallation. This happens when fast-moving particles from space, mostly protons, hit atoms in space and break them apart. This creates some of the lightest elements like lithium, beryllium, and boron, which are important building blocks in the universe. It also helps create helium-3, though some helium-3 was made during the Big Bang. When cosmic rays hit carbon, nitrogen, and oxygen atoms, they break them into lighter elements, which show up more in space than they do in the Sun's atmosphere. But this process doesn't add much to the amount of hydrogen and helium, since those two elements were already made in huge amounts when the universe began. Beryllium and boron are not made in large amounts by stars because beryllium-8 breaks apart almost as soon as it is formed. It doesn't last long. That's why these elements are mostly made by cosmic rays hitting atoms, not inside stars. To figure all this out, scientists test different ideas by working out how many of each isotope should be found. An isotope is a form of an element with the same number of protons but a different number of neutrons. By comparing the results with what we actually see in space, they can decide which ideas are right or need changing. Here on Earth, small amounts of some elements, called nuclides, are made in labs. For example, scientists can make technetium in the lab, but most nuclides on Earth come from natural processes. These help scientists figure out how old rocks are and what happened in Earth's past. Even though there's not much of them, they are very important for studying nature and the Earth's history. One way nuclides form is through radioactive decay. When big, unstable atoms break apart, they release smaller bits called radiogenic daughter nuclides. For example, when uranium-235 and uranium-238 decay over millions of years, they make smaller nuclides that finally become stable elements like lead. Also, when potassium-40 breaks down in the Earth's crust, it makes argon-40, which is a key part of our air. Most of the helium in the crust also comes from a type of decay where a helium atom is given off. Another process called spontaneous fission happens too. This is when a heavy atom splits into two smaller parts by itself, letting out energy and making new nuclids. Thorium-232, uranium-235, and uranium-238 all do this. This is how rare elements like technetium and promethium are made. Nuclear reactions during decay can also make new elements. These are called nucleogenic reactions. They happen when strong particles from radioactive decay hit other atoms and change them into something new. Neutrons made during fission can also hit atoms and change them. This helps create many elements on Earth, like neon-21 and neon-22. Cosmic rays also make new elements through a process called cosmogenic nucleosynthesis. For example, when cosmic rays hit nitrogen-14 in the air, they change it into carbon-14, which we use to date old objects. Other examples are iodine-129 and similar isotopes that are made when cosmic rays hit Earth's air. These natural processes help us learn how elements are made across the universe and how our planet works. Studying how elements are formed through space and nuclear events gives us deep insight into the universe, the Earth, and everything around us. String theory is a complicated but interesting idea in physics that says the smallest building blocks of the universe are not just tiny dots, like traditional particles, but instead tiny vibrating strings. These strings move through space and affect each other, and their vibrations decide the features of the particles we see, such as their weight and electric charge. If you look at a string from far away, it acts like a regular particle, but up close, it is actually a tiny loop or strand. One of the most important ideas in string theory is that one of these vibration patterns matches the graviton, a particle believed to carry the force of gravity. Because of this, string theory is seen as a possible answer for quantum gravity, which tries to combine gravity with the strange and powerful rules of quantum physics. Scientists are interested in string theory because it offers a possible way to solve some of the deepest puzzles in physics. Over the years, it has helped researchers make progress in understanding black holes, the early universe, and even the forces inside atoms. It has also helped math research in surprising ways, but the biggest reason string theory is so exciting is that it could be a theory of everything. One single idea that explains all the basic forces of nature, including gravity, electricity and magnetism, and the nuclear forces that hold atoms together. However, even after many decades of study, scientists are still trying to figure out whether string theory truly describes the real universe, or if it allows for too many possibilities to make clear guesses. String theory first came up in the late 1960s as an attempt to explain the strong nuclear force, which holds the centers of atoms together. But when another idea, called quantum chromodynamics, was found to explain things better, scientists moved away from string theory. However, they later saw that string theory had surprising features that made it a good candidate for explaining gravity at the quantum level. The first version of string theory, called bosonic string theory, only included one type of particle called bosons. Later, the idea grew into what is now called superstring theory, which added the idea of supersymmetry. This idea suggests a deep link between bosons and another group of particles called fermions. Over time, physicists found 5 different versions of superstring theory. But in the middle of the 1990s, they found strong clues that all 5 were really different ways of seeing one larger idea, called M-theory, which needs a universe with 11 dimensions instead of the usual 3 dimensions of space and 1 of time. In the late 1990s, scientists also found an important link called the anti-de Sitter conformal field theory, ADS-CFT, connection. This finding tied string theory to another major area of physics, quantum field theory, suggesting that the two could help each other bring new understanding. One of the biggest problems with string theory is that scientists still do not have a full and clear way to describe the entire theory in all cases. Another problem is that string theory predicts a huge number of possible universes, making it hard to figure out which one, if any, matches our own. These problems have made some scientists wonder if string theory is really the right path, or if too much work is going into an idea that might never be testable. In the 20th century, scientists created 2 big ideas to explain the universe. The first was Albert Einstein's general theory of relativity, which describes gravity and the shape of space and time on a big scale, like planets, stars, and galaxies. The second was quantum physics, which explains the strange behavior of very small particles like electrons and light particles. By the late 1970s, these two ideas were enough to explain almost everything we can see in nature, from the tiniest particles to the history of the whole universe. But even with their success, there was a big problem. These two ideas do not fit well together. General relativity is based on old-style physics, while quantum physics follows completely different rules. To truly understand the universe, scientists need a quantum theory of gravity, but trying to join the two has been very hard. String theory is one of the most hopeful ideas for solving this puzzle, but it is still being worked on. String theory starts with a very interesting idea. What if the tiny particles we think of as small dots in space are really tiny vibrating strings? Instead of treating them as points with no size, string theory sees them as tiny, one-dimensional threads that move and shake in space. These strings can be either open, like a short line, or closed, forming a small loop. The way they shake decides their features, like their weight, charge, and how they act with other particles. From far away, these shaking strings look just like the basic particles that scientists already study, fitting into current ideas of physics. But when looked at on incredibly small scales, smaller than anything we can now measure, they act in a way that could help explain mysteries of the universe. One of the most exciting ideas is that one of these vibration patterns matches the graviton, a particle thought to carry gravity. If this is true, it means that string theory naturally includes gravity, something no other big idea in physics has been able to do. Over the past several decades, scientists working on string theory have found something amazing. Different versions of the theory, which first looked separate, are actually linked through math relationships called dualities. These dualities show that what looks like one type of theory from one view might really be another type when seen differently. This led to the idea that all working versions of string theory might be parts of a bigger connected idea called M-theory. But no one fully understands what M-theory really is yet. It is still being figured out. String theory has also given surprising insights into black holes and gravity. For many years, scientists have had trouble with strange problems that come up when they try to use quantum physics to explain black holes. In the late 1990s, a big step forward came with the discovery of the anti-de Sitter conformal field theory connection, often called the ADS-CFT link. This tied string theory to other well-known parts of physics, helping scientists study black holes in new ways. ADS-CFT has even been used in other fields outside gravity, like nuclear physics and the study of materials, which deal with how particles behave in extreme situations. Because string theory tries to include all the basic forces of nature, including gravity, it has been suggested as a possible theory of everything. Many scientists hope that if string theory can be fully worked out, it will explain everything in the universe, including why particles have the weights and charges they do, how dark matter fits in, and how the early universe grew. But there are still big problems. Scientists do not yet know if string theory really explains our universe, or if it allows for many different kinds of universes. One of the hardest parts of string theory is that it is not fully understood in every situation. The easiest way to study how strings act is through a math method called perturbation theory, which works by making small guesses. But this method does not show everything about string theory, and scientists still do not know how to describe the theory in full without these guesses. Another open question is how string theory picks the vacuum state, the basic state of the universe. Without this, it is hard to tell how much freedom the theory has in shaping the universe we see today. Some critics say these open questions make string theory too unsure, while others think it is still worth studying. To see where string theory fits in modern physics, it helps to look at quantum field theory, the base of particle physics. Quantum field theory is the math idea used to explain basic particles, seeing them as bumps in hidden fields. In this idea, scientists figure out the chances of particle actions using a method called perturbation theory, which was created in the early 20th century by scientists like Richard Feynman. A main tool in this method is Feynman diagrams, which are pictures that help show how particles act. String theory builds on these ideas but makes a big change. Instead of seeing particles as points moving through space, it sees them as tiny strings. In regular quantum field theory, a Feynman diagram shows a particle's path as a one-dimensional line. In string theory, this line becomes a two-dimensional surface, showing the path of a shaking string. This change affects the math, and might explain things quantum field theory has trouble with, like gravity. But a big problem remains. String theory still doesn't have a full description beyond perturbation theory, making it hard to answer all the questions scientists want to ask. One of the most important things about string theory is the scale it works on. The length of a basic string is thought to be about 1/10,000,000th of a trillionth of a meter, the Planck length. This is so tiny that, at the sizes we can test in labs, these strings would look like little dots. Only at the Planck scale do the effects of quantum gravity start to matter, making string theory a good idea for explaining gravity at the tinier scales. String theory was first made as bosonic string theory, which only talked about bosons, the particles that carry forces like photons in electricity and magnetism. But this version had big problems, so scientists improved it into superstring theory, which includes both bosons and fermions, the particles that make up matter like electrons and quarks. Superstring theory also adds supersymmetry, an idea that says every force-carrying boson has a matching matter particle, fermion, and the other way around. There are 5 main types of superstring theory: Type 1, Type 2, A, Type 2b, and 2 kinds of heterotic string theory. Each type allows different kinds of strings, and at lower energies they show different physical features. For example, Type 1 string theory has both open strings, with loose ends, and closed strings that form loops, while the other kinds mainly deal with closed strings. In our everyday world, we know 3 dimensions of space: height, width, and length. These help us understand the shape and size of things around us. But Albert Einstein's big idea of general relativity added a shocking thought. Time is not separate from space, but is a 4th dimension. Together, they make what scientists call space-time, a 4-dimensional sheet that shapes how the universe works. In this model, gravity is not just a force pulling objects together, like Isaac Newton once thought. Instead, gravity comes from how space-time bends and curves around heavy things like planets and stars. Even though this 4-dimensional space-time model explains the universe well, scientists often explore ideas with more dimensions. Sometimes, adding extra dimensions helps solve hard math problems and makes the universe easier to understand. In fact, some science fields, like the study of materials, can be described using ideas with just 2 or 3 dimensions. But what if the universe really has more than 4 dimensions, and we just can't see them yet? Some ideas suggest that extra dimensions might exist, hidden in ways we can't easily notice. One interesting idea in modern physics is string theory. This idea says that, deep down, everything in the universe is made of tiny shaking strings instead of dot-like particles. But to make the math work, string theory needs more dimensions than the 4 we know. Different types of string theory suggest different numbers of dimensions. Bosonic string theory needs 26, superstring theory needs 10, and an advanced form called M theory needs 11. But if these extra dimensions are real, why can't we see them? One possible answer is something called compactification. This says that the extra dimensions are curled up so tightly that they are too small to see. Imagine looking at a garden hose from far away. It might look like a thin line, but if you go closer, you see it also has a round shape. An ant walking on it would notice both shapes, but from far away, one shape is hidden. In the same way, extra dimensions might be curled into shapes so tiny that we can't see them in daily life. To explain the universe using string theory, these extra dimensions need to be curled up in a very special way. Scientists think they must take the form of a complicated 6-dimensional shape called a Calabi-Yau shape. This shape is named after the mathematicians Eugenio Calabi and Xingtung Yau, who studied it. Only certain Calabi-Yau shapes would let string theory correctly describe the basic forces of nature, including electricity and magnetism, the weak and strong nuclear forces, and gravity. Another fun way to think about extra dimensions is the brain world idea. In this idea, our whole universe is a 4-dimensional brain floating inside a space with more dimensions. Imagine a soap bubble floating in the air. The bubble's surface is like our universe, while the air around it is the extra space we can't see. In this idea, particles and forces like electricity and magnetism are stuck to our four-dimensional bubble, but gravity might reach into the extra space. This could be why gravity seems weaker than the other basic forces. It might be leaking into extra dimensions. String theory also brings in the idea of duality, which means that ideas that look very different might really be two ways of saying the same thing. One kind of duality, called S-duality, says that a group of particles that interact strongly in one idea can be explained as weakly interacting in another. This means that hard physical problems might have easier answers when looked at in a new way. For example, type 1 string theory is mathematically the same as the SO32 heterotic string theory through S-duality. Another kind of duality, called T-duality, looks at how strings act in extra curled-up dimensions. It says that if a string moves around a circle of one size, it can act just like a string moving around a much smaller circle. This means that a universe with big extra dimensions might look the same as one with very small extra dimensions. Type 2, A and Type 2b string theories, for example, are really the same through T-duality, even if they seem different at first. Duality is a strong idea that shows up not just in string theory, but in other parts of physics too. A well-known example is the AD-CFT connection, which ties string theory to quantum field theory. This surprising link has helped scientists learn more about how particles and forces act at the tiniest levels. Simply put, when two theories are related by duality, it means that if you change one theory in a certain way, it ends up looking just like the other one. Even though they look different at first, they are really describing the same thing using different math tools. Another big idea in string theory is something known as branes, which is short for membranes. Branes are not just tiny dots like particles. Instead, they are objects that can stretch out in more than one direction, kind of like sheets or shapes in higher dimensions. To make it clearer, a zero-dimensional brane is simply a single point, like a tiny speck. A one-dimensional brane is a string, like a wiggling line. But there are also branes that exist in 2, 3, or even more dimensions. These are called p-branes, where the letter p stands for the number of directions or spatial dimensions the brane stretches through. These branes are not just floating around. They move through space and time while following the strange but powerful rules of quantum physics. Just like particles, branes can have physical properties such as mass and charge. They can also interact with forces in the universe, the same way that an electric charge interacts with electric or magnetic fields. So in a way, branes are like upgraded particles with more complex behavior and more room to move. One especially important kind of brane in string theory is called a D-brane. This type of brane is very special because open strings, which are strings that have two loose ends, can only exist if those ends are attached to a D-brane. Albert Einstein's famous equation is one of the most well-known ideas in all of science. It's often called the energy-mass equivalence equation. That name may sound a little complicated at first, but the idea behind it is actually quite simple and very powerful. This equation shows how energy and mass are deeply connected. In fact, they are two sides of the same coin. The equation says that energy equals mass times the speed of light squared. Now, the speed of light is about 300,000 kilometers every second. When you square this number, meaning you multiply it by itself, you get a number that is incredibly, unimaginably large. But what does all of this have to do with the birth of atoms? To answer that, we need to look more closely at Einstein's equation and understand how it helps explain how matter first came into existence. Put simply, Einstein's equation tells us that mass and energy can turn into each other. They are not completely separate things. If you have something with mass, it's like it's storing a hidden supply of energy, and if you have energy, you can also turn it into mass. This amazing idea is a key part of how our universe began and how the very first atoms were formed. To see how Einstein's idea fits into the story of atoms, we have to go back to the very beginning of everything, the Big Bang. This huge event happened about 13.8 billion years ago. Back then, the entire universe was just a tiny, incredibly hot and unbelievably dense point. There were no atoms, no stars, no planets, just an enormous burst of pure energy. In those first few moments, everything was energy. But as the universe started to expand and cool down, some of that energy began to transform into mass. That mass would eventually become the building blocks of all the matter we know today. This change from energy to mass happened very quickly. As the universe cooled, some of the energy began to turn into tiny particles like protons, neutrons, and electrons, the small parts that make up atoms. Imagine energy as something invisible, like a magical mist. As the universe cooled, this mist froze into tiny drops of matter, protons, neutrons, and electrons. These little pieces of matter were held together by powerful invisible forces. Over time, they combined and formed the very first atoms. This is exactly where Einstein's equation comes in. The energy released during the Big Bang started turning into mass. That mass didn't instantly become the atoms we know today, but it did become the simple elements hydrogen and helium, the very first and lightest atoms. These were the starting point for everything else in the universe. When this energy became mass, it didn't just create particles. It also brought into existence the forces that hold those particles together. These include the electromagnetic force, the strong nuclear force, and the weak nuclear force. Each one played a role in helping the particles come together and form the cores of atoms, known as atomic nuclei. However, in the early stages, the universe was still far too hot for full atoms to form. Instead, the protons and neutrons smashed into each other and fused together to make the nuclei of elements like hydrogen and helium. The electrons were still flying around too fast to attach to these nuclei. It wasn't until the universe cooled down enough, about 380,000 years after the Big Bang, that electrons could slow down and finally join the atomic nuclei. This is called recombination, and it's when full, neutral atoms finally came into existence. You might wonder, why did Einstein use the speed of light in his famous equation? The answer is that the speed of light is a universal constant, a number that always stays the same, and it shows how quickly energy and mass can be exchanged. Because the speed of light is so large, squaring it makes the result incredibly big. That means even a tiny bit of mass can turn into a huge amount of energy. This is why the equation is so important in helping scientists understand how stars burn, how nuclear bombs explode, and even how the first particles were created in the early universe. In those early moments after the Big Bang, particles weren't just forming one by one, they were constantly crashing into each other, changing forms and turning from energy into matter, and sometimes back again. This hot, high-energy environment was needed to make atoms possible. One of the most important ways energy turned into mass was through something called nuclear fusion. This is the same process that powers our sun today. In the early universe, particles were moving so fast and crashing into each other so hard that they could fuse together, creating new, heavier particles. For example, two hydrogen nuclei, which are just protons, could crash together and form a helium nucleus. This process is called primordial nucleosynthesis, and it happened during the first few minutes after the Big Bang, when everything was still extremely hot and dense. The particles had so much energy that they could overcome the natural forces that pushed them apart, allowing them to merge and form new elements. The energy released in these nuclear reactions was massive. It helped shape the matter that would later become stars, galaxies, and everything else in the universe. Today, atoms are the basic building blocks of everything, from the air we breathe to the stars we see in the night sky. Each atom has a center, or nucleus, made of protons and neutrons, with electrons circling around it. The behavior of these particles is shaped by the energy from the early universe, and by the same physical laws that began with the Big Bang. The question of how pure energy can turn into solid matter is one of the deepest mysteries in science. It's not just a strange idea, it's a real process that helped create the universe we live in. In the very first tiny fractions of a second after the Big Bang, the first building blocks of matter appeared. These were tiny particles called quarks and leptons. Quarks join together to form protons and neutrons, while leptons include electrons. But this didn't happen instantly. In the first few millionths of a second, the universe was still so hot that these particles couldn't stick together. They zoomed around in a hot soup called plasma, colliding constantly. As the universe cooled, the conditions finally became right for quarks to join into protons and neutrons, and for electrons to slow down and start forming atoms. This change from energy into matter was the first major step in the story of the universe. But things didn't stop there. As time passed, the universe cooled even more, and the particles started combining in more complicated ways. Even though we now understand a lot about how regular matter was created, there are still many mysteries left. One of the biggest puzzles is the question of dark matter and dark energy. The transformation of energy into matter didn't stop with hydrogen atoms. Over billions of years, the universe kept changing. Stars formed from huge clouds of gas. Inside these stars, nuclear fusion created heavier elements like carbon, oxygen, and iron. When the stars died and exploded, they spread these elements into space, where they later became part of new stars, planets, and even living things. Everything we see today, from distant galaxies to the air we breathe, is a result of energy turning into matter after the Big Bang. This amazing transformation, which began nearly 14 billion years ago, gave birth to a universe full of wonder, complexity, and life. The idea that radiation can turn into particles like protons, neutrons, and electrons is something scientists have seen not just in space, but also in labs here on Earth.